We have already seen that convolution is a really important concept in image processing. It turns out that there is a very close relationship between convolution and the Fourier transform. It's also a very important relationship. First, let's take a look at convolution once again. So here you see the convolution of two functions f and h, and the result is g. So g is f convolved with h or h convolved with f, doesn't matter. And it is defined by this integral shown here. So once again, let's use a visual illustration to show how convolution works. You take the function h, you flip it, and then you move it to a point x, shift it, overlay this function on f, find the product of the two functions, and then find the integral, and that integral, that single number, is the value of g at x. If you want to get all of g of x, you're going to take h, move it to minus infinity, slide it, and perform the same operation we just discussed to get all of g. That's convolution. And we looked at this simple example where you have the convolution of a rectangular function, f of x, which goes from -1 to +1 with amplitude 1, with essentially itself. H is the same as f in this case, and the result in this case is the triangular function, because the rectangular function slides over itself, and the area of the overlap increases linearly till it perfectly overlaps, and then it starts reducing the same way on the other side, so you get a symmetric function, which happens to be a triangle in this case. So now let's take a look at the relationship between convolution and Fourier transform. Let's start with convolution here. So g is f convolved with h, and we know the expression for convolution right here, which is the one that we just saw. Now what we're going to do is find the Fourier transform of g. And that gives you g of u in frequency space is the integral of g multiplied by e to the power of minus I 2 pi ux, integrated from minus infinity to plus infinity. And now what we're going to do is drop in the expression for g from convolution in here, and you end up getting a double integral that looks like this. And now what we're going to do is to replace u with u plus tau minus tau. So it's the same thing, but you're introducing plus tau and minus tau because that allows you to separate this expression out into two integrals that look like this, the product of two integrals. So let's first take a look at the first integral right here. You see that that is indeed the Fourier transform of f of x, right there. And now let's take a look at the second integral here. You have x minus tau here. You can replace that with y, say for instance, substitute y equal to x minus tau. So this would also become y, and the integral would then be over y, except that you would have different limits, but since the limits go from minus infinity to infinity, they remain minus infinity to infinity. So therefore, what you have here is the Fourier transform of h. So you see here that you have convolution of f with h in spatial domain corresponds to multiplication of the Fourier transform of f with h in frequency domain. So this is a very important relationship between convolution and the Fourier transform, also referred to as the convolution theorem. What it says is that if you're finding the convolution of two functions in spatial domain, that is equivalent to multiplying the Fourier transforms of the two functions in frequency domain. And using the same approach, you can also show that if you're taking the product of two functions in spatial domain, that is equivalent to convolving the Fourier transforms of the two functions in frequency domain. Very important property right here. So what does all this allow you to do? Well, if you want to find the convolution of f with h to give g, you don't have to do it in spatial domain. You can take the Fourier transform of f to get f of u, the Fourier transform of h to get h of u, multiply the two, and then you get the Fourier transform of g, and then take the inverse Fourier transform of g to get g of x. Now, why would you do this? because it turns out that there are very fast algorithms for finding the Fourier transform and the inverse Fourier transform. And so when you're looking at very large kernels or mass for convolution, often it is much cheaper, much more efficient to do it in frequency domain. In addition, this allows you to understand the effects of applying a filter. Any filter that you design in spatial domain, you can see what it really does to the frequencies in frequency domain, and vice versa. So let's look at a very simple example which we talked about before, which is Gaussian smoothing in frequency domain or Fourier domain. So imagine you have this signal right here, and you can see that there's some noise on the signal. There's noise sitting on top of the signal that you're interested in, and you wish to remove or diminish this noise. So what you can do is you can convolve the signal in spatial domain using the Gaussian kernel or the Gaussian mass, which looks like this, n sigma x. Alternatively, you can do all of this in frequency domain using the convolution theorem. And for that, what you do is you first take the Fourier transform of the signal f, you get f of u, take the Fourier transform of the Gaussian kernel, and you get this. And you can see here that the signal that you're interested in is really this one right here in frequency domain. These two little bumps that you see off to the side is the high frequency noise that you actually want to remove. And this Gaussian kernel, or its Fourier transform, we know the Fourier transform of a Gaussian is a Gaussian, and what this does is that it acts like a low-pass filter. It passes frequencies in this region, and it essentially kills all the frequencies that are high. And so now what you're going to do in frequency domain is essentially find the product of these, because remember, convolution in spatial domain is multiplication in frequency domain. So find the product of these two Fourier transforms, and you get this. And you can see here that the little bumps that correspond to noise are pretty much gone. And now if you find the inverse Fourier transform of that, you end up getting this clean signal. And for comparison, if you look at the original signal with noise, it looks like this.